Well, thank you everyone for coming today. I will be discussing a novel redesign to metadata collection. So to begin, we have to ask, what is metadata collection? Why is it important? And how is it important to uh, genomics and HuBMAP as a whole? So let's start with collection. What is data provenance? Data provenance is where a piece of data comes from. It's kind of like the historical ledger of data. And how is this relevant to genomics? Well, genomics data is collected after a complex set of protocols, all of which can affect the quality and the authenticity of the data collected. And then metadata describes, explains, and makes it easier to manage information in informative resources. So what kind of metadata are we collecting? We are collecting specifically RNA sequence samples. So kind of like the sample ID, the harvest by, which describes the researcher who collected the sample from the source material, be it a culture dish or tissue. The species constitute the species from which the source material was derived, and then the strain is the strain of the source animal. So in the culmination of data, there are problems that arise. Inputting data can be rather labor intensive, especially because it happens when experiments are already completed, making it the task of recalling pre-recorded data very time consuming. And researchers sometimes dread this obligation because it can be seen as an inconvenience to their work, to the basis of their work. So we, the Kim Lab, seek to remove this feeling by proposing a solution where experimenters, lab techs, and the like are able to capture metadata conveniently and while they perform their experiments. Which leads me to my objective, capturing metadata to establish data provenance for HuBMAP before, during, and after procedure while using a user-friendly and uncomplicated input interface. So in analyzing the previous method of data encapsulation, I saw that in capturing a sample of data and that is essentially what we're trying to do, collect attributes of samples. So in collecting samples, many of the attributes were analogous. So the similar samples would be categorized into groupings of similar properties and features, and then the groups themselves would share common features, which could then be categorized themselves into batches. So creating a hierarchical scheme as shown on screen. A batch can have a given set of attributes common to all groups. All samples of a group could then share similar fields, allowing a top-down approach to metadata collection, which would make inputting the data much simpler. To further explain, I've captured some images of my hierarchical approach method. So imagine only having to log onto your device of, let's say, 100 samples. So you log onto your device during lab procedure, you have 100 samples. You create groups of samples and batches of groups. So in the batches, you add a field attribute and instantaneously assign an attribute of 100 samples. Or in groups, you add a field that assigns 45 of the 100 samples. So this significantly reduces the task of individually filtering through and entering the data manually. It also reduces the risk of inputting errors. So as you can see in my hierarchical setup, we have three banks in a sense, three banks. We have the batches, the groups, and the samples. And so we're able to create a batch, and for a given batch, we're able to create as many groups as we desire. And for a given group, we are then able to create a given number of samples. As shown here, we can create the batch. This is the batch view. Then we have the groups where we can see the individual samples in the groups, and then we can see the samples and the nicknames. And from there, we're able to create different batches, different groups, and different samples. To continue in the data entry view, each level on the approach will have its own level of attributes, which will affect the scope of the given level. Meaning in each level, we'll have a species that can be edited within the selected vision parameters. So as we can see, we can look for a certain batch, and with the given batch, we will then be able to input different data. So the same is for the strain, where these attributes also have built-in logic. So depending on what you pick or your selection different options are presented. So we have here a strain picker for the strain, where we can see the different types of strains that we can select from. And depending on the option that you choose, you can have different images show up. So now to achieve these views to implement this logic, I had to learn Swift UI and Xcode, which is a programming language and a simulation environment, respectively, that allowed me to create these apps, which make metadata collection mobile. In addition, I had to become familiar with IIS core data, which is an objects graph and persistence framework. Essentially, it allowed me to persist and save the data upon entry locally to the device. So with the knowledge of core data and the Hub of God family and the Kim lab, I was able to make a functioning design that I plan to persist in the future. And with that, I would like to acknowledge the NHGRI for their sponsorship, the NIH, specifically Zarina, Ajay, and Julie, for everything they've really done for us as interns. We really appreciate their mentorship and their time and willingness to help us through everything. I would also like to acknowledge and thank Dr. Kim, Dr. Fisher, and Dr. Nordgren for just their support and guidance and the app designs to kind of working through with me. And I would like to thank the Kim Lab as a whole for their support and guidance as well. Thank you, everyone.